I bought a data logger because I was like, you know what? I mean, a motorcycle is essentially like a little dyno. I could put sensors on it. It's pretty easy. And if I can log it, then I can just look at my computer and kind of record everything that's going on. And so that's how I got started.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Chloé Lerin, who is a powertrain performance engineer specializing in engine development for Harley Davidson. She's also involved heavily with Aimsport as a data analysis specialist, and she's working specifically in the MotoAmerica Championship. So we're talking here about superbikes, not cars for a change. And as we find as we go through this conversation with Chloé, there's some really interesting and specific differences between analyzing data and actually getting that data in the first place on a motorbike versus a car platform. Probably shouldn't be too much of a surprise, but there's some really interesting aspects as we get into this. In this interview with Chloé, we find out about her background, how she got involved in engineering, how she built a passion for motorcycles and motorcycle racing. We also find out about her day job at Harley Davidson, and on face value, most people might not think that Harley Davidson are perhaps at the cutting edge of engine performance, but after this interview, I think you'll have a fresh perspective on exactly what is going into these modern engine designs. Specifically, we also talk about emissions, which is becoming a really, really important aspect, obviously for OEs, but also for us in the aftermarket. We then dive into data analysis and what's involved in setting up a data analysis package for a competitive motorcycle. And we talk here as well about the minimum viable product, essentially the minimum number of sensors you're going to need in order to get really reliable data that can help improve your performance. And then once you get a little bit more familiar with that, what sensors you're going to want to add and in what order, so that you're not overwhelmed both budget-wise and in terms of the raw data that you're collecting when you're first getting started. Before we get into our interview, for those who are fresh to the Tuned In podcast, High Performance Academy is an online training school, and we specialize in teaching people topics such as engine tuning and engine building. And we do this with online video-based training courses that you can take from anywhere in the world. You can use the coupon code podcast75, and that's going to get you $75 off the purchase of your very first HPA course. We'll put a link to that coupon code in the show notes, as well as a link to our list of course material. All right, let's get into our interview now. All right, welcome to the podcast, Chloé. Thanks for joining us today. And as we always do, I want to get started by finding out a little bit about your background and specifically how you started forming a passion for the automotive industry. So let us know.
Yeah, so I'm French, and I grew up in a farm in France. I was introduced to motorcycles by my grandpa when I was a little girl. I didn't really touch motorcycles for a long time. I was really not interested in any motorsports, not exposed to any motorsports when I was a kid. And but I knew that I wanted to do a job that was pretty active, but also pretty intellectual. And so I thought that the answer was going to be to join the military. I wanted to be an officer in the army or a pilot. I went to military high school for 3 years and decided that was really not for me. So I decided to go to engineering school to study planes at the time. My very first internship in that engineering school was for a company called Safran, which makes a ton of stuff, but also has a division that makes turbofan engines or airplane engines. So that was my very first exposure to thermodynamics, which I really liked. And France has this really cool program in a lot of engineering schools, which is called apprenticeship. So usually you see apprenticeship for trade work or trade schools, but it's been declined onto engineering schools in France, and I think in Germany as well. So after my first 2 years of school in France, I was able to find an apprenticeship, and I ended up at John Deere. So I started working in test cells in 2012 on John Deere tractors. And instead of doing any performance stuff, I was actually doing NVH. I started really getting an understanding in, okay, where does the sound come from on engines? How do they vibrate?
Let's just talk about that term you mentioned, NVH, for those who haven't heard of that before. What's that mean before we sort of dive deeper into what you're doing there?
So NVH means noise, vibration, and harshness. And so it is the study of the effects of noise and vibration on everything, but in this case on engines. So it still requires work on dyno, and a lot of the sensors that we're using for that are microphones or accelerometers. And it's particularly important because depending on the RPM that you're running at, you're going to enter natural frequencies, and that's going to excite different areas of your engine. So for tractor engines, when I was at John Deere, we had the diesel particulate filter that was on top of the engine in some cases, and at some RPM, it would actually vibrate in the opposite direction, which would cause bracket failures. So it was really important for that. We also had, there are noise regulations. And so in a tractor engine, everything is gear driven. And so that's a big source of noise that needed to be tamed down in a way. So that was my very first exposure to, my second exposure to engine really, and thermodynamics, and my first exposure to engine dynos.
It sounds like at the moment we're about as far removed from motorsport as possible, though.
Absolutely, absolutely. So I continued down that path, and actually through John Deere, I came to the US for the first time. So in engineering school in France, we have to do an internship abroad. Working for John Deere in France, that naturally led me to coming to the US. So I think it was January, my first time in the US. I was minus 45 when I landed, and that's Fahrenheit and C. It's about the same thing. And so I did an internship in Iowa, and so from there, still in NVH, I really started to want to understand more about combustion. I was like, okay, so noise and vibration is caused by combustion. How do I study that? And when I was there, I met a lot of engineers that were really, really good. And they all come from the same school, which is the University of Wisconsin in Madison. So I applied there. And then as soon as I graduated from my engineering school in France, I went to do a master's in Wisconsin, where I studied combustion. So I kind of see my career as a funnel. So it really started from, oh, this is cool, I want to study things that move, and then down to combustion. I then graduated with my master's, where I studied spark ignited small engines. And part of my project was sponsored by Harley Davidson.
Okay.
So then I was riding a motorcycle, and I kind of skipped that part, but as soon as I was in age to afford my first motorcycle and take the test, I took the test and got my first motorcycle on April 1st. Actually, my mom hated that. And when I moved to the US for my master's, I had the choice to either buy a car to get along in Wisconsin or buy a motorcycle. And eventually, I just naturally bought a motorcycle. But, I couldn't do any track events. I didn't really have the money to do that. So I just rode around. And I was fine. I was really not attracted. I didn't know anything about motorsports at the time. So graduated, went to try to get a job actually in a motorcycle company in Europe. I tried a bunch. I think maybe the fact that I had an American degree didn't lead to anything.
Because you wouldn't have been able to do a comparable degree back in Europe?
I think there are a lot of comparable degrees. I think, and I might be wrong about that, but I think a lot of European schools will hire from, a lot of European companies will hire from schools that they know. And you see the same thing in the US. You know the value of the engineer. So I never was able to find a job in Europe. So I started working in the US. And as a matter of fact, I actually got a job in Japan for Honda motorcycle. I didn't make the move there. Personal decision. But so I started working for Cummins, that makes diesel engines. So again, removed from motorcycle. And the reason why is because in the US, you need a visa to work. And Cummins is a really good company that sponsors a lot of visas. I worked there for a little bit, worked on nothing that ever made production. It was a lot of R&D, really interesting work, probably 7 years ahead of production in my team. That's really what we were working on. Yeah,
I'll just stop you there. It sounds like so far between John Deere and Cummins, a lot of your practical hands-on experience at this point has been around compression ignition diesel engines as opposed to spark ignition gasoline engines. With the degree, your master's, combustion analysis, does that sort of cover both styles of engines? Because there are some significant and obvious differences between the two, correct?
Absolutely. So I don't think there is anything more complicated than a compression ignition engine or a diesel engine. But my master's is in mechanical engineering with a focus in combustion, we're studying combustion. So no matter how it's created, there are actually advanced combustion modes that are trying to mix both, whether it is, I don't know if you've ever heard of HCCI or RCCI, reactivity control compression ignition. We're actually really trying to use the benefits of diesel with the benefits of spark ignition and put them together. So actually my school was the lab, the Engine Research Center in Madison, which is a lab that I was working in, is known for those advanced combustion modes. So no, we're definitely using both. And actually, when I was at Cummins, there's a couple papers on that. I was not working on diesel, not at all. I was actually working on alternative fuels. So except for when I was doing NVH, a lot of my work actually has been on direct injection and spark ignition. So after that, I actually got the opportunity to go work in research. So I took a job at Oak Ridge National Lab, which is a big government lab that was initially created for the Manhattan Project in the US. And they have a transportation division where they're doing a lot of really advanced engine work. And there I built a couple test cells. I was working on pre-chamber ignition, which was really interesting with natural gas, on a DD13, so a Daimler DD13, 13-liter engine.
So pre-chamber, you're talking sort of the turbulent jet ignition style that's current in F1?
Yep. Okay. So turbulent jet ignition is, I think it's patented by Mala, but we were using a Mala system. So worked quite a bit on that, and then COVID happened. And when COVID happened, that's when I actually made the move to start working in motorsports. And things that I missed, we were talking about my education. But when I got my first paycheck working at Cummins, my first job, I essentially just bought a race suit and did my first track day. So it's when I first took my motorcycle on track.
Straight in the deep end.
Right, exactly. At this time, I just knew that I wanted to learn how to ride my motorcycle fast, and I wanted to do it in a safe way. So I'm a late bloomer. I really started when I think I was 26 at the time. But that was my very first taste of motorsport.
So let's just pause there. So, I mean, my own experience in motorsports and probably most of the people that I deal with who are currently in motorsports have sort of had that passion instilled in them almost from birth. And it sounds like, other than you said your grandfather kind of got you interested in motorcycles at a younger age, it doesn't sound like you really had that specific motorsport passion until later. That's how it went down?
No, absolutely not.
So you woke up one day and thought, hey, you know what, I want to learn to ride fast?
I always liked motorcycles, and I realized that the roads that were around me were not very interesting. And I was like, you know what? How do I do this? I didn't know about track days. I only thought you had essentially racing and then race schools. So I started looking into that. But yeah, I just wanted to, spend my money into something for some reason. It's the best way to lose all of your money, I guess, getting into motorsports. But what's funny is my parents live 2 hours from Le Mans. And every single year we would see, all of the RVs and the caravans going to Le Mans. And my parents would just mention that, they're going to the 24. Okay, cool. And I've never been. So
2 hours away and you never went.
Yep. So it's a personal goal of mine to actually ride Le Mans at some point. But so I started doing track days. I think it was 2018. And interestingly, I mean, I didn't have the vocabulary to talk about motorsports. I didn't really understand everything that was going on, everything that I was feeling on the bike, and it was a little bit overwhelming. So I bought a data logger because I was like, you know what? I mean, a motorcycle is essentially like a little dyno. I could put sensors on it. It's pretty easy. And if I can log it, then I can just look at my computer and kind of record everything that's going on. And so that's how I got started. I was a little bit overwhelmed, a little bit tired of trying to listen to people telling me what to do. And
decided to get a little bit more granular with the data so you could figure it out for yourself. Which obviously leads into what you're sort of doing on your weekends as a data acquisition engineer with Aimsport. We'll park that side of the conversation for a moment because we've got two very separate areas of your life and experience. So we're going to come back to the data acquisition side of things. But let's sort of go back now. You've given us the sort of background and a bit of a history of how you've sort of got to where you are, and you are currently working with Harley Davidson. So What's your current role at Harley? What are you in charge of?
So I am a powertrain performance engineer at Harley Davidson. This means that I work on developing engine configurations and selecting engine configurations. And most of my work actually focuses on engine dyno.
Okay.
And my entire world essentially focuses on engine dynos.
By the engine design, are you talking here about the engine in its entirety? That's your role?
Not my role. This is the role that my department
Sure.
is taking care of. Everything is very segmented. So you're going to have people that are developing cams, and then other people that are going to focus on the design of the combustion chamber. My role is actually dyno process. So automating dyno processes. We have, so you can be on your dyno and you can start just running your engine, and through all of the sensors you have, cylinder pressures and your temperatures, you sort of know where your combustion phasing is. So you could just punch the numbers and then try to fill all of your calibration tables by hand, or you can just acquire a lot of data and then through an algorithm spit out calibration tables. So a big part of my job is to improve those codes. So a big responsibility that I have is torque mapping. So now you know that a lot of engines are going from the alpha N, or throttle based calibrations to torque based calibrations, and we're working on converting all of our engines, all of our ECUs, essentially from throttle based to torque based, and we're doing that through a series of tests, or like a series of data acquisition. We run the data through my algorithm, and then essentially what it does is it reverses the base of the calibration to give you essentially torque-based calibration.
The torque-based mapping is something that's obviously far from new, and the OE world really has been embracing that for a while. So there's a couple of elements. You mentioned alpha N there, or throttle-based mapping. Can you just sort of break that down a little bit for our listeners who haven't heard of alpha N before? What is that in a nutshell, and why is it utilized?
So in a nutshell, alpha N means that you are looking at your throttle position. So what is your throttle position angle? How much air are you putting into the engine, and therefore how much fuel you're going to put into your engine.
So essentially the throttle position becomes your load axis for
Your load.
fuel and ignition tables, correct?
Right, correct.
Okay, so this is a very common strategy for engines that use individual throttle bodies, which I'm definitely not deep in the motorcycle world, but that seems to be the way. Is that right?
Yes, I think so.
Okay, so versus in an automotive application, at least in the OE world, individual throttle bodies are rare, not non-existent, but definitely rare. And typically we would instead have a plenum chamber with a certain volume and then a single throttle body, which the more common technique there is where the manifold absolute pressure after the throttle body is monitored. So can you give us a rundown on why that technique does not work when we get rid of that plenum chamber volume and we instead have a single throttle body? Individual throttle bodies.
We are using a single throttle body for 2 cylinders on our engines. So you're taking your throttle position as an input, but you're also looking at your manifold pressure, like you're saying. We are converting from the speed density to the torque mapping, or like the torque based mode, like you're saying. So speed density is essentially your ideal gas law, where you're trying to see how much air is going into your engine. We're still doing the same thing in torque mapping, but what we're trying to do is essentially see how much torque the engine can output when the throttle is fully open. And then we're mapping this at different values of throttle, and then we're reverting that. So essentially we have a table that's converting throttle position or airflow into torque. The reason why we have torque mapping, in my understanding, really is we have so many engine management strategies, whether it is for traction control, engine braking, knob control, and all that. And it is much easier to operate in a way where you're requesting a percentage torque reduction than actually just going and saying, oh, I need to close the throttle, or I need to lower, or I need to retard my spark, or I need to cut fuel. So by having a strategy that is based on torque. You can just say, I want less torque right here. And your engine is going to deliver less torque. Parts of the strategies in different layers are going to tell the engine to cut the torque in different ways.
Sure.
And it's really, to me, it's a lot easier to use for vehicle management strategies or engine management strategies than alpha end / speed density technique.
That makes a lot of sense. This, I can only assume, also works hand in hand with drive-by-wire.
Yes, you have to. Essentially, yes, because you're what we call the throttle grip instead of the accelerator pedal position in the motorcycle world. Your throttle grip is essentially detached or decorrelated from what the throttle position actually is, but it is only applicable when you have a drive-by-wire.
So then you've got the rider or driver input is basically becoming a torque request that the ECU will then process and decide what to do based on the current strategy.
Yes. And I mean, if you're looking at a rain map, for example, that's it's a very good application of what we're calling the torque shaping. So once you have your maximum torque curve, then you can shape it down for different ride modes. So if you're just turning on the rain mode, then even though you're going to go to 100% throttle on your grip, your delivery is going to be a lot less than that.
Yeah.
So.
And again, I apologize. I don't have personal experience or very, very limited personal experience riding motorcycles, but from people that I do deal with who are into them, particularly dirt bikes, a lot of the time, which is very different to cars because of the relative power to weight ratio of bikes. In a car, we're always after more torque or more power. And often, from what I understand, again, in a motorcycle application, it can actually be beneficial in terms of shaping the way the torque is delivered to maintain traction. So it's not always about getting more, it's about controlling the way the torque is delivered. So am I on the mark there?
You are, absolutely. Motorcycles are very interesting for that because you're putting, let's say an average of 70 kilogram rider on a motorcycle that's, 170 kilograms. And, those motorcycles, if you're taking a sport bike that, the things that we're seeing the most on the track, they're outputting 200 horsepower. So you're putting, you essentially have a total mass of, whatever this is, like 250 kilograms and 200 horsepower. So your power to weight ratio is absolutely gigantic. And you really have to manage that. And in another way, Harleys are very different because we're really talking about a cylinder displacement that's really close to cars. They're essentially car engine as far as displacement goes. But on a sport bike, you have oversquared engines and they're revving so fast that knock is really not that much of an issue on race bikes. But what actually is an issue is how do you get that power to stay on the ground? How do you get that rear wheel to stay on the ground? So we're looking at very similar strategies as far as, an engine works the same way anyways, regardless of the engine. But we're looking at very different ways to apply the power and manage the power as compared to a car.
All right. Now, specifically with the Harley Davidson, your position there, without trying to sort of offend anyone who's a Harley Davidson fanatic, my own sort of background growing up and seeing Harleys on the street, when we think of Harley Davidson, probably the image that pops to mind is sort of a hairy biker type and maybe not necessarily maybe cutting edge performance in the engine department. So it sounds very much like that's all changing. Is that a case? Is that sort of a new direction that Harley have had to take in terms of current technology relevance and making sure their bikes remain emissions legal? Is that sort of angle?
I think it's a very interesting question. We keep saying that the customer base of Harley Davidson is dying. The general public has been saying that for 100 years, I think. And it doesn't seem like it's the case. It seems like those people, the customer base that is dying is actually being replaced every time. So if I am in my 30s and I'm riding a sports bike right now because I think it's cool, maybe I don't want to give up riding motorcycles when I'm older and I just end up buying a Harley CVO, which are the top of the line Harleys. So I think there is a customer base that's still there. Regarding the type of customers, you're right. There is this big following of Harley Davidson and this very typical Harley Davidson rider. But I think Harley is really trying to expand that. So to your point, I think Harley is trying to change. We, when you think about Harley Davidson, you're thinking about air cooled engines, push rods, and we recently released, I think it was a couple of years ago, the Revolution Max, which is completely liquid cooled. It's overhead cammed, has phasers, has 4 phasers, and is not, obviously not push rod. So,
Sorry, with that term you just used there, phases, you're talking about variable cam control?
yes, yeah.
Okay.
So,
Just wanted to clear that up.
not the lifts, but the cams are actually moving to change the phase. So we are really taking a step in a new direction, I think.
Do you face any backlash when you make a fundamental change from the likes of air cooled to liquid cooled? Does that sort of give you any backlash from the existing Harley customer base?
We see it. We really see it from some people that are, what you would call a purist Harley Davidson customer. But the new Revolution Max actually has been very well received. A lot of people that had an adventure bike, because it actually goes into an adventure bike that Harley Davidson made, which is a big departure from Harley Davidson type of motorcycles. A lot of people that have that bike are really happy with it. A lot of people that have the competitor, which is the BMW GS, tend to just sell it and buy American. As far as the American market, an adventure bike is also a lot more suitable to a lot of other countries. As far as riding in Europe or going on an adventure somewhere else, it's a very good bike. So we're definitely making changes. I think it's a little bit slower than I personally would like to, but we have to go with what the customer wants and what the survey is, essentially what the data is telling us.
Yeah, absolutely. Just coming back to one specific element there, you mentioned that change from air-cooled to water-cooled. When you're dealing with an air-cooled engine specifically, and this is an area I haven't had much to do with, but I thought we'll talk to you about it since we've got you here. Are you, in terms of cooling the engine, are you focused more on the designs of the fins and the airflow around those fins to cool the engine, or is there an element of using additional fueling as well, running a richer air fuel ratio than typically you would need in order to use some additional fuel to help in cylinder combustion cooling as well?
You have to use a really good design. If you're running fuel rich, then you're going to have to deal with emissions. So I can tell you offline that we don't really care about emissions, but we don't care about emissions because we have three-way catalysts. The three-way catalyst only works when you're around stoichiometric. It's you have to dither between a little bit rich, a little bit lean, but you have to be around that lambda of 1 in order for your three-way catalyst to take care of your emissions. So
you couldn't run it rich because the catalyst wouldn't work.
Exactly. Only in some areas, when you have to compromise. But you have to have a really good design. And the Milwaukee 8, which is the newest generation of that big V-twin, is what we call precision cooled. So you have the cylinder head is actually either oil cooled or water cooled, and then the rest of the cylinder is air cooled. So you still have the big fins. It's Harley Davidson is a really interesting company because there is such a huge design and styling aspect. Styling is a very big thing, a very big part of the company. So yeah, it's the very first time that in my job as an engineer in research and development, I've had to care about how the engine looks.
Yeah, it wouldn't probably be the first sort of go-to thing. And if we look at an automotive-based engine, typically you pop the bonnet or the hood and everything's covered in plastic. You don't actually really see the engine at all. Obviously, dramatically different on a motorcycle. So I do get that. We haven't actually talked so far about the size of the team that is involved in this sort of powertrain development. Can you give us a sense of scale?
The whole company, the whole Harley Davidson corporate is about 5,000 people, which is not that big. To put that in perspective, when I was at Cummins is entirely a powertrain company. It was about 60,000 people. Wow. So in Harley, the powertrain team, I would say, is maybe counting the calibrators, my team, performance, and the designers, I think it's maybe 50 people, about that.
That's quite small.
What I wanted to note earlier, what's really interesting about Harley is when I came into the company, it was about a year and a half ago, I thought that I was going to work with engineers that kind of looks like the customers, that were just diehard Harley Davidson customers. And to my surprise, everybody in my team and everybody in the extended calibration team is some kind of motorsports enthusiast. And so we have, I have a coworker that's a flat tracker. I have another one who rides dirt bikes on the side. I have another one who builds a race car. And so you're really with, essentially just engine enthusiasts and motorsports enthusiasts that really want to, push the company forward in terms of technology. And what's really interesting about Harley Davidson is our engines are actually pretty technologically advanced. I mean, we have, like I said, we have combustion phasers. Oh, sorry, we have cam phasers. We have engines that are delivering, interestingly, a lot of power for being air cooled. We're working with really interesting challenges where we have to keep an older looking engine, but we still have to deliver performance and emissions and noise. So it's quite challenging. It's actually very interesting.
Yeah, absolutely. Do you think, in terms of your team all being genuine motorsport enthusiasts, do you think that's really essential for bringing that passion into their day job, your day job, and advancing the company? Does that really help, as opposed to just purely having an engineer who may be very skilled at what they're doing but doesn't necessarily have that passion?
I think you need a little bit of both. You need the people that are ready to tackle very specific, very deep projects. And then you need to have the people that, are very passionate about the performance aspect, or maybe have more of an overview of where the company should go or what we should do. As a matter of fact, actually, Harley Davidson has a race team. We have, within MotoAmerica, there is a section or a class called King of the Baggers. And it's essentially Harley Davidson against Indian baggers. So those 640 something pounds motorcycles turn into a race bike.
Okay, interesting.
And I've had quite a bit of involvement with it. I'm responsible for the testing of the engine. And so now you're talking about a project where emissions doesn't matter, noise doesn't matter, durability matters, but it doesn't have to be the same durability requirements as a road engine. And we're now trying to extract as much power as we can from our Harley Davidson engines. And it's been extremely interesting, because when you're talking about maybe a 3-year development for an engine that's going to hit the road, now you're talking about, development that takes weeks. So from simulation, design, testing an engine dyno, testing on the chassis dyno, testing on the racetrack, we're talking about just weeks or months.
And you said it's a sort of a 3-year design cycle in the production bikes. Was that what you said?
About that, yeah.
Okay. Yeah, it makes sense. You can do things a lot quicker. Obviously, your restrictions would be far reduced as well. Now, let's just sort of move back to the design criteria around the production motorcycle engines. Most people would sort of think that you're targeting a specific amount of power, a specific amount of torque, and maybe a torque curve, torque delivery, etc. And that's as far as it goes. But in the OE world, we've got a lot more that you need to consider. You've mentioned NVH already, but then there's emissions and noise. So, what's the sort of hierarchy of those aims? What's the driving parameter that you must keep in mind at all times?
If you're asking our team, performance is going to be the most important. If you're asking my manager, noise and regulatory emissions are going to be very important. So, at the end, we need to deliver a product that suits all of the requirements. So take it as a Venn diagram of noise, emissions, performance, and actually you could add style on it. I don't think there is anything that's more important than the other. It's all a trade-off. So eventually, it's a lot easier to pass emissions with an engine that doesn't deliver a lot of power. We still want to get the power aspect out of it. So to me, it's the job of a calibrator. It's the job of an engine performance engineer. It's really trying to find that area in the Venn diagram where everything works out.
Yeah, absolutely. I think, obviously, as you say, everything, all of those elements are important, but I guess at the end of the day, it doesn't matter how well you've done in terms of power, aesthetics, etc. If the emissions and noise exceed the regulatory limits, then that engine's never going to production, correct?
Exactly. It doesn't go. Yeah.
Now, you've mentioned the emissions and the three-way catalyst that you're using, and I think there's obviously as time moves on and the pressures of the regulatory limits, both the OE world as well as in the aftermarket world, change. Obviously, there is more and more focus around making the engines emissions compliant. And I think there's an expectation in the aftermarket industry that we can go and put in a large cam with a huge amount of duration and overlap and basically all the other changes we may want to make in a performance world. And then the calibrator can just sort of fix all of that when it comes times for emissions testing and make the engine emissions compliant. It's not quite the case, though, is that you actually have to have a basic architecture that could be emissions compliant before the calibrator can make it so?
It has to be. You still have to have a pretty decent base. So, for example, as far as design of the engine, something that really helps emissions can be the phasers, the cam phasers. So, cam phasers are actually really interesting because you can change the intake and the exhaust cam relative to each other. Oranges don't do that. You move both at the same time, so the overlap is fixed. But depending on where your overlap actually is, you can affect the engine in very different ways. So cam phasers are used for emissions, are also used for power. So depending on where you're placing your overlap, you can actually reduce your effective compression, or you can also just like play with the amount of residual that it's in your engine. So residual are every burn gas that are trapped into your cylinder. If you're keeping an amount of burn gas into your cylinder, it actually helps you reduce emission. You see that with EGR in other production engines. So it's essentially internal EGR. So those are actually elements of design that are integrated into the engine to help with emission reduction or power management. Yeah, the calibrator can't do everything just with the computer and the calibration table. We definitely need to have some aspect of the engine design, as far often combustion quality or breathing of the engine that will help you achieve
Sure.
that.
Again, sort of more specific to the Harley market, you've mentioned sort of the style, the aesthetics is important, and the sound of the engines is obviously important as well. And again, everyone listening has probably heard Harley sort of rocking down Main Street, and that exhaust note is very specific and often also really loud. And particularly that sort of idle quality you get from these engines, a lot of that the sound comes down to the cam profile, the overlap. Again, does this sort of fly in the face of the emissions output, and is there a sort of a balance there between getting the desired exhaust note and still keeping the engine emissions compliant?
It has to be. A lot of the noise actually on the engine comes from the angle, the firing angle. So Harleys have a firing angle of 45 degrees, or at least the big twin engine. With the Revolution Max, we've had a departure from that, and now we're actually using a 60-degree angle. So the new engine that I mentioned earlier, that's liquid cooled overhead cam, has phasers. That engine actually has a different V angle, therefore has a different sound. But if you're just focusing on the main Harley engine, the Milwaukee 8, what you would imagine as being the more traditional engine, I would say the exhaust design is a very big part of it. The muffler that you're going to use is going to be sort of the last part of the regulatory noise. So you have a lot of leverage because your angle is fixed, is going to be 45 degrees. You have this like potato sound, that's very tied to the Harley. Then the exhaust design is going to take care of that note. We have some really interesting testing facilities. We have what we call a semi-anechoic chamber, so essentially a big sound room that's insulated on the sides and the roof, where we can put a motorcycle and then simulate what we call pass-by. So it's a test that simulates the motorcycle, moving forward. And we have an array of motorcycles and microphones, an array of microphones, and then a dyno inside the big room. And so technicians there tend to test a bunch of different exhaust mufflers.
Okay, let's move back to the sort of work that you're doing in terms of how that sort of actually looks. And so I'm guessing you start with some software tools to actually simulate an idea before anything's actually manufactured. Is that correct?
Yes. So we never really start from scratch. We have generation of engines that we're building from, but the first step is simulation. So we have a software called GT Power that can simulate an engine, so you can actually do some kind of design experiments in it and try different geometry aspects of the engine. You have, and this software is a lot more complicated than that, but we also have CFD simulation tools. So computational fluid dynamics, where you can actually see how much an intake manifold is going to flow, how much the head is going to flow. We have, simulations for camshafts, etc. So we have that, and then from the simulation, we actually go to a prototype. The prototype goes into engine dyno, which is really where my work starts. An engine dyno, we generate base calibrations. We select the hardware that we want to proceed with. So there's going to be a head, a cam, different manifolds, whatever. So we then generate a base calibration and a base configuration, and then we take that engine and we give it to the calibrators. The calibrators then put this engine into a motorcycle, and they're going to refine the calibration. They're going to make sure that it passes emissions, and they're also going to work on drivability, because I can deliver the maximum torque curve and the best calibration ever for maximum power. At the end of the day, you still need to make sure that the bike is driving properly, and you need to make sure that traction control works properly, wheelie control works properly. Although wheelie is not so much of an issue on a Harley, but all of the different driving modes are also very important. So vehicle dynamic people and the vehicle calibrators then take care of that after us.
Okay.
And then we go through different project phases. You're going to have the prototype, the development, vehicle, etc.
You sort of mentioned before, the cycle might be around 3 years, but I'm assuming there's a number of iterations that go on within that period between the start of a project and actually something rolling out the production line and into the showroom. So, first of all, along that process between the software simulation and then the dyno validation, sort of how well do these simulations actually work out? Essentially what I'm asking is, how close now is the software? How good is it at sort of you having the confidence that when you hit the dyno, you're going to get your numbers that you saw in software?
In my experience, which is mostly on the race engine, it's pretty good. I'm sure you've heard the saying "garbage in, garbage out" when it comes to simulation.
I was going to talk about that as well.
Really, exactly. So when you have really good inputs, which as an OEM, we have a pretty good setup for this. I mean, we can measure everything that all the information that are proprietary, we do have them. So as long as you have good input, you're going to have pretty decent output. Examples recently were camshafts and intake snorkels. So the big boot that you see outside that leads into the throttle body. We tested different configurations, and the results that we saw in dyno were pretty close. There are other elements that were completely new. We didn't really have a lot of previous data, therefore our inputs were not as good, maybe, or they worked in a different way that we expected, and the simulation was a little bit off. So it really depends on how much data you have, how much input you have, and how much experience we have to set up the experiment. But in general, it's pretty good.
I guess when you're dealing with what you were just saying, sort of some elements that are relatively new, so you don't have the really high quality data as an input into the software. But of course, as you iterate, you're starting to generate that data, so the model starts to become closer, more accurate.
Yes.
In terms of the actual dyno process, so talk us through what you've got available to you. What sort of dynos? I'm assuming you're talking engine dynos here solely, no chassis dyno testing. So what are the dynos, and what are the inputs that you've got access to in the OE world?
So our dynos are, so specifically engine dynos, we have a huge array of sensors that are divided in, I would say, two categories. We have the high-speed sensors and the low-speed sensors. High-speed sensors is everything that can be indicated on your encoder. The encoder was going to pick up your crank angle degrees. So whereas on a flywheel you'd have like 30 something minus a couple teeth, an encoder is going to have 70 to 100 data points. So you have about, about 10 points per crank angle degrees.
Oh, wow. So very, very fine resolution.
Very, very fine resolution. So on the fast speed, so everything that's crank angle indicated, we're going to have cylinder pressures. So we have two cylinder pressures. We're going to have our manifold pressure, our exhaust pressure, injections, and injection timing, and ignition. So all of those are usually the high speed. And then if we want to do crankshaft dynamics or valve train dynamics, we also have that available. And then everything on the low speed side is something that we're going to acquire at a pretty high sample rates, but it's not going to be as fine as looking at a single cycle combustion cycle.
Sure.
So it's all over temperatures, torque measurements, etc.
Okay. Just coming back, you mentioned crankshaft and valve train dynamics. Can you sort of elaborate on specifically what you're talking about there?
So these would be really close to what we're doing in NVH. So you would put strain gauges on the valve train, and that would allow you to actually see whether the valves are bouncing. On the crankshaft, that would allow you to see if the crankshaft has any deflection, for example. Yeah, so really, really looking at how your hardware is moving relative to your crank angle degrees, essentially.
Sure. I think, generally most people would assume that if you look at a crankshaft from either a car engine or a motorcycle engine on the bench, it's nice and rigid, nice and stiff, so it's not going to flex. But of course, at high RPM with a lot of cylinder pressure, there is that potential to flex. So it's interesting that you've got the ability to monitor that with strain gauges. Moving into the combustion pressure analysis, I'm quite interested in this element. It's something that I'd dearly love to have the opportunity to play around with. So, I mean, it's self-explanatory. You're monitoring the pressure inside of the combustion chamber. Before we get into what you're using that data for and how you're sort of breaking that down, how do you achieve that data in the first place? You can instrument a spark plug with a pressure sensor or fit one directly into the combustion chamber. Which method are you using, and are the pros and cons of either?
So we're not using the spark plug instrumented system because we have heads available to us. And actually, the Harley Davidson engines are awesome for that. There's a compression release valve on the heads, and so we use that to put our cylinder pressures in it, cylinder pressure transducers in it. So we don't have to drill the heads. If you're taking any other engine, it's complicated to put cylinder pressures because first it's really expensive, but the transducers are generally fitted in the combustion chamber, and you have to drill the heads to put the cylinder pressure transducer. So if you were to do any development in your shop, then you have to sacrifice the head, and it's not ideal. The Harley engines are awesome because we just replaced the compression release valve and we put our pressure transducers in it. So we have direct access to that. There's just like two companies that make those sensors, essentially, usually AVL or Kisslers. And then this comes, so it sends a signal to an amplifier. The amplifier then sends a signal to the the fast data acquisition system. So it's a pretty expensive system.
Yeah, definitely not sort of in the realms of the average sort of aftermarket enthusiast, for sure. Although there are some systems now that certainly, while I've been in the industry, have come down to the point where for maybe some of the higher end aftermarket performance workshops, could be justified as an expense. I just wanted to dive back in. You mentioned compression relief valve. I mean, there's probably a hint in what it does in its name, but what exactly is that, and why is it incorporated?
So I actually learned the ins and outs of it not too long ago, but it's simply to help the engine start. So when you're cranking your engine, you're not fighting a vacuum in the engine, in the cylinder when you start. Yeah.
All right. So not actually used once the engine's up to sort of operating speed.
Not that I know of. No.
Okay. Perfect. All right, so now you've got this data and you've got that high precision encoder wheel that's looking at exactly whereabouts you are in the engine cycle at any time. What is that data telling you? How critical is it to your decision making from there?
It tells us everything. I mean, it's really incredible. The first reason we use it is to calculate our ineffective pressure. So because we know our volume and we know our pressure, then we're able to get our PV diagram, which gets us so much information. It actually tells us how much pumping, so negative torque we have, how much indicated ineffective pressure we have, which is essentially the work that the piston is doing. It tells us about our combustion phasing. So in the world of OEM calibration or combustion people, we really don't talk much about spark advance. We always talk about CA50, and CA50 is the crank angle at which your 50% burn has happened. And this is, to me, it's much better to use than spark advance because it's much more uniform throughout your engine map. So you're always going to target, it's about the same number. It's about 6 to 8 degree after TDC, and this is generally our target. So because you know your temperature, because you know your volume, because you know your cylinder pressure, you actually know how much fuel you're burning and where. And so you're able to use this value as your target for, start of ignition, essentially.
Sure. So that drives your spark timing as opposed to looking for a specific cylinder pressure and angle.
Exactly. We choose CA50 because what we call combustion duration is usually 10% of manufacturing burn to 90%. So CA10 to CA90. And this is usually, if you're looking at heat release, so the heat generated by your fuel energy, it's usually about a constant slope. So CA50 is the middle of that point, or the middle of that slope. And yeah, that doesn't move so much. But the time from your ignition to your CA50, or the time from CA50 to the end of your burn, can actually move a lot. And so that's why your ignition timing is going to change throughout the map quite a bit. And looking at, we're getting pretty deep here, but your combustion speed or your flame propagation speed is dependent on a lot of things in your cylinder. So it can be your temperature, it can be your air motion into your cylinder. So all of that is going to affect the speed at which the flame travels in the cylinder. So anyways, so we use CA50, it's a lot easier, but we also use cylinder pressure for knock. We have knock sensors, but we have to calibrate those knock sensors because they're essentially little accelerometers, little microphones that you put on the cylinder. The information that a knock sensor gives you is a frequency. You need to tie that frequency with like a knock intensity. And knock is easily seen on a cylinder pressure trace because you're actually seeing ripples. So you're seeing some kind of a resonance inside your cylinder. So you can measure how much knock you have because you know what your cylinder pressure looks like when it's not knocking. And then you see how much oscillations you have when you are knocking. And so we have a ratio. And this ratio is what we use as a target for kind of our knock threshold.
And I talk to a lot of enthusiasts who think that all we need to do is bolt a knock sensor to the engine, and particularly with the aftermarket ECUs that offer knock control functions, which is just about all of them these days. Our job's done and we never need to worry about knock. But of course, as you're just saying there, those knock sensors need to actually be calibrated so that the ECU knows what a certain level of activity is and where knock is starting to occur. So, typically in the aftermarket industry, we're doing that using audio knock detection, but that brings in a little bit of sort of,
like magic?
Well, I wouldn't say magic. We like to say there is no magic in the tuning industry, but it does come down to a little bit of experience on the part of the tuner and then being able to distinguish between background engine noise and knock. Now, I'll admit sometimes that's clear as you just can't miss knock it. It's so obvious, but in a lot of it, in situations, particularly with race engines with open exhausts and solid valve trains, there's a lot of mechanical noise there, so it does get a little bit trickier. So obviously the holy grail there, if we've got that in-cylinder pressure monitoring, there's no mistake. We know when knock is occurring. In terms of these Harley engines, how much of an issue is knock? I'm assuming from what you're saying that it's something you definitely can end up running into.
You definitely run into those. There are big engines, so therefore, and they don't rev that fast. In the posted maximum RPM for the big twin engine, which I work on the most, is 5,500 RPM. So knock tend to happen when you have really high pressure and high temperature in your cylinder, but also when you're giving it enough time to happen. So if you have high compression ratio, high cylinder pressure, you have this propagating flame front, and then you have all of your end gas that's residing in front of it. This is a perfect recipe for knock, especially when you're at, you have everything coming together. So, like any engine, it's a problem. We're not turbocharged, so there's that on the side of pressure. We're a little bit safer, but it is definitely a problem. It's something that we have to account for.
How do you deal with the calibrations in terms of, obviously, there's not a lot of control that you'll have once the bike leaves the factory in terms of the fuel that the owner decides to put into it. Some owners will always choose the highest octane that they can get, and others maybe look at it as more a budget consideration, and you're going to tip in the cheapest, nastiest fuel available. And obviously there's a broad range in terms of knock sensitivity based on the octane of that fuel. So how do you deal with that? Are you dealing with essentially detuning the spark map to account for the worst possible scenario, or maybe going with a more aggressive calibration that's going to deliver more torque and power and be better suited to a higher octane fuel, and then relying on the knock control strategy in the background to keep the engine alive for those who are tipping in 91 octane?
I don't know so much how I can speak of that because it is also the work of the calibrators that are delivering the calibration. But like any OEM product, you have to account for a little bit of a margin.
Sure.
You always have a safety factor. So whereas in racing, we're going to allow the engine to knock a little bit more. In OEM, we're going to make sure that we're below an audible level of knock, so the customer cannot hear it. The knock level could be safe. We still don't want the customer to think that there is a problem. So it's whatever threshold you decide that is safe for the customer, whether it's audible or whether it's a safety concern for the engine. You're always going to have a margin there.
Let's talk about that as well, sort of what level of knock is tolerable. And again, I think probably a lot of people new to the tuning industry, they've heard of knock. If they understand it, would think that absolutely under no circumstances do we want any level of knock. But there's knock and then there's knock. If you have the benefit of being able to look at cylinder pressure traces, there's light, low-level knock that's unlikely to do any damage, particularly any damage quickly. And I liken that to probably all of us have heard some sort of old 1970s Toyota Corolla being driven up a hill in fourth gear by granddad, and the thing's audibly knocking, but it's probably going to do another 100,000 miles without any damage. On the other hand, if we take 1,000 horsepower, 4-cylinder, highly boosted, turbocharged engine, and we run that into knock, it's probably going to cause some issues pretty quickly. So can you talk around that a little bit?
Yeah. So again, it's the spectrum. So you're going to have, like you said, you have the light knock, you have the heavy knock, and you have the super knock. So a super knock is damaging, but a super knock only happens when you have a case of pre-ignition. You have the light knock, which is fine until you run into a condition where it's constantly knocking. So if it's constantly knocking, I kind of like to explain it as imagine a little bit of a fireworks into your cylinder. So if you have a firework in front of your flame front that's propagating, a little bit of it can be okay. Too much of it can be bad. And if you have a knock that's leading into more knock, then eventually the duration at which you're experiencing those knock events is going to be a problem. So, a little bit of knock here and there is okay. Sustained light knock is not really desirable. Heavy knock is absolutely not desirable, and super knock is usually it's a engine ending event. It's destructive.
Yeah.
And I think there's a lot of misunderstanding on what a pre-ignition actually is.
I think there's also a lot of confusion around pre-ignition versus knock. I get people referring to it as pre-detonation. Those terms are getting mixed up so much. Without trying to get too far off track, can you sort of clear up the difference between pre-ignition and a knock event?
Yeah. So I wish I had some cylinder pressure traces to show, but this is a podcast, so I want to try to do my best. So a knock is what we call end gas detonation. So you have your flame front. So imagine you have your spark timing event. You have a kernel that's developing into a flame. The flame is propagating down to your cylinder, and then it's compressing and burning the fuel, that's the air and fuel mixture that's in front of it, which we call the end gas.
I'll actually stop there because I think a lot of people assume that when that spark event occurs, we just get essentially an explosion inside the cylinder and all of the fuel and air is burned instantly. Now, if we've been listening to this podcast, we already know that's not the case. But as you mentioned there, it's the flame front propagates out, and it's actually that moving flame front that then ignites the fuel and air that's unburned ahead of it. So I just wanted to stop there. That's our normal combustion. That's what we're hoping to achieve. So I'll let you continue now.
And this is for a spark ignited engine, so a gasoline engine.
Of course.
So as your flame front propagates, then everything that's in front of it that's unburnt could get into some situations where it gets hot, and it is going to ignite in front of it. It's going to auto-ignite in front of the flame front. So in that case, you have the flame front propagating down, and then you have this little ignition that's happening in front of it that's going to propagate and hit the flame front. And so you're going to have one or two or more flame fronts that are going to collide with each other. The heavy knock would be if you had the same thing happening, but the end gas detonation or auto ignition is so hard that it's becoming becoming supersonic. So you have, it is subsonic, but it's faster than a light knock. A pre-ignition happens before your spark timing event. So you're compressing your gases, your piston is going up, and then you're creating pressure and conditions that are so high that it doesn't even wait for the spark to happen. It starts igniting. And this is really bad because your crank is pushing your piston up, but then you have a flame that's starting that's really fast because it had high pressure and temperature, that it's starting to push your piston down.
And this is happening much earlier in the combustion cycle in comparison to knock.
Yes. So knock happens after your spark timing event has happened. This is happening before. So your spark plug hasn't fired up, but you're creating that flame that's starting to travel really, really fast, and it's pushing in a very small volume because your piston is going up. It's pushing the mixture of air and fuel. So now you have that pre-ignition that's propagating, and then you have really fast, and then you have a knock that's happening. And so, but that knock is so hard that it's actually supersonic. So now you have a wave that's hitting the flame that's propagating, or what we call deflagration. And now you have extremely high cylinder pressure that's developing right away when your piston is pretty much up. And so that tends to destroy your engine. You have really high temperatures, really, really high pressure. Your crank is working against it, and you tend to just destroy it. The reason
so essentially you've got cylinder pressure occurring that the components inside the engine were never designed to deal with, as well as the high temperature.
Yeah, and there's a delta that's being kind of given as a threshold for what we qualify as super knock, and I think I forgot exactly, plus 15 MPa, I think, something like that, on top of your maximum cylinder pressure.
So above and beyond what your normal operating cylinder pressure would be, and you said 15 MPa above that.
I think that's
considered a super knock event. Okay. Again, we've got pretty down in the weeds with this. I don't want to sort of consider this to be an all-encompassing discussion on knock, pre-ignition, and super knock, but I thought it would be interesting just to get a sort of a base understanding of it from you.
Mm-hmm. And we don't really know why pre-ignition happens. There's a lot of work that's done actually at Oak Ridge National Lab. So I encourage people to go and look for publication from Oak Ridge National Lab, and specifically from their exploder. But we think that it mostly happens during low speeds. So low speed, high knock. That's what we call it sometimes, low speed pre-ignition or LSPI.
And that low speed pre-ignition has become more prominent with direct injected engines becoming more mainstream, hasn't it?
Direct injection, downside boosted, yes.
And we are actually hoping to get Derek Splitter on the podcast, and if we can do that, then we're going to go much deeper into this topic. So, as I say, this is just a cursory sort of discussion around the topic. I just wanted to take a moment to interrupt this interview with Chloé. And if you're enjoying what you're listening to, I just wanted to detail a course package that I think you'd really love. That is our tuning starter package. So for those who are interested in learning about tuning, and it doesn't matter if you're interested in tuning an aftermarket standalone ECU or maybe reflashing a factory-based ECU, this package has got you covered. It includes our EFI Tuning Fundamentals course, which teaches you the principles behind how an engine operates and how the electronic fuel injection system works. This is really key to understand before we actually dive into tuning. We then include our practical tuning course. Here, you get the choice between our practical standalone or practical reflash tuning course, depending on what you're more interested in tuning. And we teach you how to tune the ECU, and it doesn't matter what particular ECU you are tuning or what engine for that matter. The way the engine operates and the way we approach the tuning process remains identical. Each of these courses also include a step-by-step process that you can apply to your own tuning. And this breaks down what on face value might seem like a bit of a daunting task and makes it really easy in bite-sized steps to get through and get a completed tune that's going to offer you great power, torque, and most importantly, great engine reliability. Both of these courses also include a library of worked examples where you can watch the step-by-step process being applied on a real-world tuning job. We vary the type of engine we're tuning as well as the tuning platform we're using to give you experience on a broad range of systems. We also are including our Understanding Air-Fuel Ratio course, which in my opinion is probably one of the most misunderstood topics in the world of EFI tuning. And on top of that, you're getting 24 months of gold membership, which gives you access to our fortnightly members webinars as well as our webinar archive, where we've got 300 plus hours of existing content covering topics on engine tuning, engine building, wiring, race car setup, data analysis, just to name a few. You'll also get access as part of this to our private members only forum, which is the best place to get answers to your specific questions. This entire package is the best way to get you up to speed tuning. It is $417 US. Remember, if you haven't purchased a course before, you can use that coupon code podcast75 to get you $75 off the purchase of this package. We also have a 60-day no questions asked money back guarantee. So if you don't like what you see, no problem, let us know and we'll give you a full refund of the purchase price. Let's get back to our interview now. I think, Chloé, we'll move on from here because this is only part of your sort of job or part of what you're involved in motorsport. And I really wanted to dive into the other element, which is your data acquisition side of things. So if we can do that. Now, you already sort of mentioned that when you started doing these track days, you pretty early on decided to adopt a data acquisition system. And I'm guessing what you're doing now kind of grew from that. So can you give us a bit more information on how you got involved with Aimsport and the data acquisition work you're doing now?
So when I first started doing track days, like I said, just kind of vocabulary barrier led me to get my own little data acquisition system so I could review my own sessions. And so I purchased what's called a Solo 2DL from AIM. It's a little box that you set up and you can read CAN data from your ECU. So they have a large library of ECUs that have protocols available. But it also has a GPS and a little gyroscope in it, so you can actually record your lap times and review your data as a function of your GPS data. So you can see lap times, you can see your GPS speeds, you can see your lean angle all throughout the lap. So I got that, and I started getting pretty good at using it. Started helping other people, setting them up on their bikes, but that was, I think, 2018, 2019, and COVID hit. So when COVID hit, I was still working at Oak Ridge National Lab, and I was not allowed to go work in person. So I'm an experimentalist at heart. I was working in dyno. I was always building test cells, setting up systems, and I got to a point where I couldn't do any of that. So I had a lot of time in my hands, and I went to attend my very first pro race, MotoAmerica race, with a couple of friends, and initially just helped. I can't just stay and do nothing. So I helped pick crew. And the racer that I helped was not using any data acquisition system on his bike. And I think at the time it was really not that common for little bikes. They were just using their transponder, looking at their splits, and that was it. So I offered him, I said, I could join you to the next event, and I could put a lap timer on a little data acquisition system on your bike, and maybe we can go from there. And he trusted me. He said yes. So from this, we went to Indianapolis Raceway, Motor Speedway, and I set the little GPS lap timer on it. We reviewed data after every session, and he got better. So he hired me on for the 2021 season, which I did with him. And I think he ended up 9th in the championship, in the Twins Cup championship. And after that, it just went rolling. So I was making a few posts on my Instagram. I was making videos with my own data, trying to process everything on MATLAB and showing an aerial view with the GPS data for where my motorcycle was around the track, showing the race line, etc. And AIM reached out. They asked me if I wanted to do a webinar about motorcycle data, which I did. And that was essentially the beginning of a really good collaboration. So I went on and did, I think, 3 or 4 other webinars, each of them going a little bit more in depth. And from that, I got a lot of people asking me for help in the paddocks and just in general, just reaching out, asking to do data review with them. And so because I had so many people just asking me all the time for help, I asked AIM if I could represent them in the paddocks, essentially. And so they offered to send me to every racetrack during the MotoAmerica season and do tech support. Okay. So now I'm the motorcycle specific AIM trackside engineer at MotoAmerica, which is awesome.
Is there a team involved, or are you Aimsport essentially for MotoAmerica?
I am Aimsport for MotoAmerica.
Okay, great.
So I mostly support Junior Cup up to, I would say, Super Sport. So we have different classes, like any racing. It's going from small twin cylinder 400cc bikes up to so we have the Twins Cup, which is essentially a higher displacement but still twin cylinder, and then we have a Super Sport, which is around 600cc, and that can be actually 4-in-line or twin cylinders.
Okay,
and so it's kind of a new class. Superbike is way more specific because they use aftermarket ECUs. So Motec, Harley ECU, and they tend to have the data acquisition system that goes with it.
So not a standalone additional data acquisition system.
Right.
All right. Let's come back and I want to sort of maybe focus around when you got started with the data acquisition system on your own bike with that AIM Solo 2DL, because we've actually got one of those units which we've used for some of our data acquisition courses. I've found it to be a really powerful and cost-effective tool. One of the things you can start with is essentially just the unit itself and GPS lap timing, and that's going to give you data based on the GPS inputs, speed, acceleration, etc. But then you can start adding other elements as well. You talked about getting engine data in via CAN communication, so that could give you engine RPM, throttle position, etc. But then you can start going a little deeper with these data acquisition systems as well, particularly with the more advanced ones, and adding your own sensors. What do you sort of think when you're getting started is essential? Because I know that when you start adding more sensors, yes, there's more to analyze, but it can also end up overwhelming someone who's new to data acquisition and data analysis. So what's your sort of take on that? Keep it simple or go advanced?
No, keep it simple at the beginning, for sure. A lot of people are using the Solo 2DLs as simply lap timers, which kind of hurts my feelings. So
it's leaving a lot on the table if that's all you're doing with it.
Exactly. So I've gone on a mission to try to educate people on everything they can do with it, but keep it simple. So your lap time on the Solo 2DL actually includes your speed around the track. So you can just download that on your computer and you can start seeing just your speed around the track. You're able to see where you start accelerating and where you start decelerating. You can see your corner speed, which is very important, and where this minimum corner speed actually happens. Are you on the apex? Are you a little bit too early? Are you a little bit too late? So the first thing that you can do is disregard the engine data and the CAN data. Just start focusing on your GPS speed and then compare yourself to, yourself, another lap, another good session that you had, or a buddy of you that's on a similar bike. And then see, where you're wasting time, when you're actually better, see how fast you're accelerating, etc. The solo 2DL then, the next step after that is really looking at rider input. So, okay, you see where you're going faster, you see what your speed is, but you want to understand how you're achieving that. So now you can use a math channel to calculate your lean angle, and then you can look at your throttle position, you can look at your braking points, you can look at your shifting points, and you can look at your RPM. And I think this is really the package for somebody who really wants to progress and doesn't really want to tweak the bike. So it's kind of the rider improvement page where we're seeing, okay, are you using the gears fully? And are you using your entire RPM range? Is your gearing right? Because on a motorcycle, gearing is very easy to change. But let's say your motorcycle is correct and properly geared for the event that you're at. Are you using all of your gears? Are you shifting properly? Are you getting on the throttle fast enough? Are you braking fast enough? So you have this kind of school book idea of what a throttle position trace should look like. And it's the same in a car, right? What efficient braking looks like. And we have those periods of coasting. And it's kind of like the second thing that you're looking at after you're looking at your RPM, your GPS speed and your trajectory. How much coasting do you have and how do you reduce that? That would be, and that is what actually I start with. And then if we decide that the rider is actually pretty good and he's really trying to achieve, good transitions between throttle and brakes, he's using his gears as much as he can, then you move to, okay, how can we allow you to go faster? Is our gearing right? Is our RPM, in 6th gear? Are we touching the maximum RPM at the end of the front straight? Yes, no, then you're going to affect gearing. Is my rider trying to get to full throttle but can't because his rear wheel is spinning and we can't transfer the power to the ground? So in that case, is it a chassis issue or is it an ECU issue? And in some cases, you just can't touch the ECU, so you're not going to be able to affect traction control. So how can we affect that through chassis and suspensions? And then you start moving on. And, if you start in the first class that we have is Junior Cup, those bikes are making, I think, 50 horsepower or a little bit less, probably less. And the kids are, 15 or a little bit older, a little bit younger. You want to focus on rider technique. But then when you go up in class and you start having more rider aids, you're starting having riders that are more experienced. You look at their data and you know they're good. You know that they know what they're doing. So at that point, you start asking yourself, how can I make the motorcycle work for this rider? How can this rider really use all of the power that this motorcycle can actually give him or her? And in that case, that's where you start looking at traction control, engine braking strategies, wheelie control, etc. So how can this rider deliver the power to the ground, essentially?
Just essentially optimizing or matching the torque delivery with the amount of traction available from the tire. Now, you mentioned earlier lean angle. Obviously very specific to a motorcycle. If we've got a lean angle in a car, then something's gone horribly pear-shaped. But lean angle, and you mentioned a math channel to calculate that. So can you sort of dive into that a little bit? And how does that, is there an optimal lean angle? Does that depend on the radius of the corner, the specifics of the corner, the motorcycle and the rider? I'm totally out of my league here.
So a motorcycle doesn't turn by turning the steering wheel, or even by turning the handlebars. Really, it turns by leaning. So we don't really have that much of a the yaw, but we have a lot of lean angle. So we want to know how much lean angle the rider is using, and lean angle is limited by the profile of your tire. At some point, you run out of thread, you run out of contact patch. So, and the thing is, the more you're leaning, the more your contact patch is reduced. So you cannot have maximum traction and maximum throttle at the same time. Otherwise, you're just sending yourself out of the track. So we're always looking at that. How up and down is the motorcycle? How far lean is the motorcycle? The maximum speed at which you're going to take a curve is dependent on lean angle, essentially. I mean, if you want to take like for the same curve, if you want to take it at a slow speed, you're going to be able to hug that curve very easily. If you want to increase your speed, it's going to push you out. So you're going to have to increase your lean angle, essentially. So there is a physical limit to how fast you can go around a curve, essentially. But what's interesting about a motorcycle is your wheel speeds. Your wheel speed has to be corrected for your lean angle. So as our tire profile is round contrary to a car, it's not a flat contact patch. It's a round profile. So as you're leaning, you're getting on the side of the tire and your circumference of your tire is going down. So your wheel speed is actually not accurate anymore. So although like one rotation of your wheel is covering less ground because your circumference is smaller. So now if you want all of your strategies to be accurate, when you're looking at traction control, wheelie control, etc., you absolutely have to correct your wheel speed for your lean angle. And then you're going into a ton of simulation rabbit holes because how big is that contact patch? How much does your speed and your force on your tire affect the circumference of your tire? And then that's something that, I think only MotoGP really is doing, trying to model the tire. And even at an OEM level, we're trying to model the tire. And I think it's the most interesting thing in motorcycle engineering ever.
The potential complexities there are making my head hurt already. But I mean, that's something, I wouldn't have even considered until you mentioned it, is that changing circumference of the tire. And now, I'm guessing there's two elements to this. I mean, for one, you want accurate wheel speeds, front and rear, in your data acquisition. But then that information, as you've sort of alluded to there, also needs to be accurate and corrected inside of the engine control unit if it wants to instigate traction control properly. And am I safe to assume here that the tyre profile front and rear means that the lean angle changes the relative front and rear wheel speeds, or
Yes.
do they sort of, okay, yeah.
Yeah, the size of your wheel is the same, but the width of your tire is very different. I mean, you have it's a 120 on the front, or 180 or 200 on the rear. So yeah, you can't just keep the same value of wheel speed because the relative speed is changing. And like you guys know, in the car world, the difference between your slip value, the difference between your front and your rear is really important. So if your rear wheels start going faster than your front wheel, then you're slipping and you most likely need traction control. So, but the thing is, if your front wheel starts going up in the air, which is not a problem in cars, your front wheel stops going fast. So the value drops, but it means that the difference between your front and your rear is actually also increasing. So what tells you that you're spinning on the rear or that you're actually lifting the front? And so that's where your IMU is really important.
Okay.
Also, because are you pitching or are you straight? And is it your front wheel or your rear wheel that's actually different?
All right. So IMU, can you elaborate on what that is for those who've never heard that term?
Yeah. So I forgot exactly what IMU means, inertial measurement unit or something like that.
Yeah, I believe so, yeah.
So the IMU is a little device that is able to sense your yaw rates, your pitch rates, and your roll rates. So it's a mix of gyroscopes and accelerometer, I believe. So it's about to sense your acceleration in the three axes, essentially. So an IMU is very important, especially on a motorcycle, because we're operating in basically three axes. I mean, we don't have that much of a yaw, but we're definitely, operating in 3D where you can lift the front wheel a lot. So, and we have lean angle, which would be the roll rate. It's a really clever little device that really tells you, where your motorcycle is as a function of, ground,
time and space,
yeah.
So are you then using some advanced math channels based on the output of that IMU to start correcting some of these elements, like the wheel circumference and hence wheel speed that you've mentioned already?
So depending what system you're using, if you're just using an AIM data acquisition system, and depending the ECU, depending of the ECU that you're using, you would hope that the ECU has a channel that's already corrected.
Perfect.
For wheel speeds. Oftentimes, when you're just doing data acquisition, the easiest signal to get when you're reversing a CAN protocol or a CAN signal is the raw speed. So in most of our AIM protocols that are available to the customers, we have raw wheel speed. And so if you want to really understand where your motorcycle's at, like what your strategy is doing, you're going to have to create that math channel.
Okay. Now, I'm guessing at this point, some of the people listening are probably, their eyes are starting to glaze over, and they're thinking, well, I've got no chance of creating that math channel. But I just want to be clear. I mean, we're talking about some more advanced analysis techniques, and particularly if you're just getting started, just that AIM Solo 2 DL with no additional sensors and none of the engine data coming from the ECU, that's going to give you so much ability to improve your lap time in and of itself before you ever start looking at these more advanced techniques, correct?
Correct. And AIM actually made a bike angle channel, math channel. It's already calculated in the background. The only thing you still have to create it, but you can just pull the function bike angle, and you're only inputting its GPS speed and GPS gyro are the names of the AIM channel. So you can just create that. It's going to show you your lean angle, and then you can just plot your raw wheel speeds. So just looking at your lean angle and your raw wheel speeds, you'll still have a pretty good idea of what's going on. And you can see it from the data. If you're wheeling, your front wheel speed just goes down really fast.
Now, one of the I believe the most powerful and simplest analysis options available, and this is across the board, just about every data acquisition system is going to give you this, is a variance channel in terms of you can bring up a lap, be that maybe you put in a scorcher lap in qualifying and you want to figure out what you did different to your other laps where you couldn't quite get that speed. Or alternatively, if you've got the ability, as you mentioned earlier, to grab data from maybe a better rider on your bike or the same machinery and analyze where exactly the improvement of lap time's coming from, that variance channel is a very powerful way of doing that. Can you just sort of elaborate on that variance function a little bit?
Yeah, so I think we're actually calling it, it's like I forgot, it's like a time difference, you're right. It's a variance
Time
channel.
delta, maybe? I can't quite
Yeah,
remember.
it's some kind of time delta. Yeah. And you can actually have it in instantaneous or in compounded or cumulative time. But it's it's usually your first tool when you're looking at two different laps. So you're able to see, you could take the derivative of this essentially, and that would give you where you are exactly in each sectors, but or in each section. But essentially you're looking at it, and when the difference in lap time is large, you'll see this variance channel just increase. So you can actually just look at this channel first and then see where you're wasting time or where you're gaining time essentially, and just like focus on those areas. It's just a quick view really that tells you where to focus on.
I mean, for me, I also find when you're dealing with a novice driver, or at least a driver that isn't super experienced, not a professional, you want to limit the sort of feedback that you're giving them, because if you sort of give them 10 things to work on for the next session, there's not a chance in hell they're going to be able to remember all of that information. So for me, when you're looking at that variance channel, like what you're saying, when there's a big difference in lap time at a particular point, you'll see, if you plot this as a visual graph, a time distance graph, you're going to see the slope or gradient is going to be very, very steep in those areas. So, I mean, I'll try and sort of take maybe 2 or at the most 3 of the areas where the slope of that gradient is the steepest. So that's where the rider is losing the most lap time, and then just dive into those a little bit more and say, okay, well, in this area, you can see that compared to the fast lap, you're braking, 20 meters earlier or whatever it may be, or and just give them those 3 areas to work on, and then over the series of a few sessions, like that's normally, I find at least, a pretty good way of getting that person dialed in. Does that sort of match your experience?
That's exactly what we do too. Yeah, you can tell a rider to just go focus on the 10 or 15 corners that there is on a track. It's just not possible. So yeah, pick your battles, pick the most important one. What's also really cool is that helps you quantify how much time they're losing. So by looking at how much time they could be gaining, it's also a really good argument maybe for them to say, hey, in this place you're losing, let's say, zero point 0.4 of a second. 0.4 of a second, that's what would move them on the grid from 10th place to 3rd place, for example.
Mm.
So it's riders think in lap times a lot, and so you can say, okay, this is going going to be the two corners where you have to focus on, and this is how much you can gain.
Yeah, yeah. All right, moving into sort of the higher level systems. We've already talked about the IMU, but could you sort of maybe mention any other more advanced sensors that you really like to have available if budget and capability is there?
Mm-hmm. So starting package for a motorcycle would be the Solo 2DL, but then the next step would be a brake pressure sensor. The throttle is usually available directly from your CAN protocol, so that's fine. And then you're going to do front and rear brake pressure sensor depending on your motorcycle. Smaller motorcycles and riders barely use the rear. It's mostly front. So, you could just focus on the front. And then the next two really important ones are going to be your suspension potentiometers. So front and rear suspension potentiometers, that would get you a really long way as far as setting up the motorcycle and rider abilities, or rider coaching. If you want to go a little bit further, you need a lambda sensor that allows you to see if the motorcycle is tuned properly. And you could let's say you can make some changes on the ECU that allows you to do it. Tire temperature sensors, external and internal. So we have tire pressure monitoring systems that you can put internally on the rim that gives you your local temperature and pressure. And then infrared sensors that you can put outside to actually look at the carcass temperature. I think that would be a really good start.
I'm just interested with the infrared tire temperature data because, that's something we use sort of at the higher end of car racing as well. But that's more in line with starting to optimize some of your alignment settings. Obviously, tire pressure is an element there, but mainly I'm talking here about optimizing camber settings, so making sure that you've got a flat tire contact patch mid-corner, and essentially we're getting reasonably even temperatures between the inside and the outside edge. We know that we're working the entire width of the tire contact patch and getting the most out of the tire. That's not really an element with a motorcycle. There is no camber. Essentially, the rider's creating that camber. So, is that more around the tire compound and tire pressure as opposed to any setup element?
So, I'm starting to set up mine on my motorcycle, and I'm actually considering where I need to put them. Going back to that round profile of a motorcycle tire, how many sensors do you put and where do you put it? So I actually am considering putting 3 sensors on the rear because you need to target each area. When you're looking at a motorcycle tire after a session, you usually have those cold tear or hot tear marks on the side, or just any sign of wear, and they're almost always going to be on the side of the tire because you never really straight up and down unless you're on a front straightaway or on a straightaway. So a lot of, I call them suspension gurus because I really don't come from that world, will be able to look at the wear marks on the tire and say you need more compression or rebound, or you need to go to a different pressure or a different compound. I personally don't really know how to do that, so I would want to look at the temperature of the tire as you're going around the track and as the wear increases, and correlate that with the pressure inside the tire. And really try to understand how much we're working the tires, how much, correlate that with spinning. Am I losing contact as my tire is spinning, and how does that increase my temperature? And really at this point, I'm thinking about it in a very theoretical way where I want to continue chasing that rabbit hole about tire simulation. So I have not seen a lot of teams using it unless they're at the superbike level. There are a few teams that are using TPMS sensors. Let me rephrase that. I think there's a lot that is left on the table when it comes to tire management.
No doubt.
I think we could use a lot more on a motorcycle, especially when you're not limited in number of sensors. I think there's a lot more that could be done to understand characteristics of the tire during a race weekend.
Yeah, I agree. That's absolutely the case. And I think what's important to point out here, and I have asked you specifically about some of the more advanced sensor options, but again, for those listening, understand that less is more, particularly when you're getting started. And I do see a lot of people here in motorsport in New Zealand as well as around the world, maybe they've got a pretty decent budget and they'll sort of tick the box and get all of the sensors that are available. But if you don't understand what that data is showing you, they're not really going to help you. And then again, you can just get overwhelmed by the sea of data that you don't know how to analyze. So it's really important to sort of start small, and as your skills progress, sort of build up your senses to give you that sort of next insight into the next element that you want to analyze. Before we move on, one last question on the data analysis side of things. Are there any of the more advanced functions in the Aimsport system in terms of and analysis of the data that you've acquired that you're sort of leaning heavily on?
Math channels, for sure. I like to create my math channels. The simulation aspect of it is very limited, but I'm trying to calculate different gear ratios to see how that would affect my wheel speeds, essentially. So math channels is probably the biggest one. Scatter functions, scatter plot is really interesting when you're looking at, or you're trying to sort of get an understanding of what your engine map looks like. So you can actually look at, lambda distribution as a function of throttle position and RPM. So this is scatter plots.
So let's just talk about that. So, I mean, if we're looking at, a snapshot of maybe the bike accelerating down a long straight, and we're looking at lambda versus RPM, obviously that's going to be wide open throttle. That's useful, and this goes for cars and bikes. But, you might have a race that's maybe 15 or 20 laps long. Maybe it's an endurance race that's obviously even longer. So that only gives you one snapshot. But the scatter plot, you can actually start analyzing that data over the entire race if you want, can't you?
Exactly. Yep.
So then you've got some outliers, but you start to see a bit of a trend of mainstream, where are we actually sitting? Are we good or whatever? And then start bringing in throttle position over that as well.
Yes. So when I'm building my data acquisition layouts, I always have the time and distance to look at, time distance plot to look at all the different channels of GPS speed, wheel speeds, etc., rider input. I have the same time distance base tab for suspension. So what's my suspension velocities? You can use the histograms to actually look at your distributions. But then I have, obviously the layout of the track and the trajectory of the rider. Is my rider using the track as much as possible? Are we hitting the right apexes? I have scatter plots to look at my engine health, or sort of try to get an idea of if my calibration is correct. Another one that's really good is what AIM calls a channel report, which actually gives you just like basic statistics per lap. So your suspension averages are really good. Your maximum RPM is really nice to track. Engine temperature. What was your maximum engine temperature? And you can track that per lap, so you can see if it increases. To me, it's a really good summary page to just look at just the overall health or overall behavior of your motorcycle and how that actually is affected throughout the laps.
I like to use those channel reports as well for elements such as engine oil pressure and maybe battery voltage as well, engine temperature and oil temperature as well. But again, rather than trying to track a particular channel through 30 laps of data, it's going to give you that snapshot of where the minimum and maximums were, and as you say, how that's sort of progressing as you go sort of lap after lap, whether the temperatures are plateauing or still continuing to climb.
Right, exactly. So that's about it. You can always do a little bit more, depending on what problem you're trying to solve. So I like to approach data acquisition with, you start from a very simple data acquisition system and a very few sensors, and then you just start running into limitations, and you just tell yourself, oh, I wish I had wheel speeds so I could actually see if I was slipping and losing traction. Then you start adding wheel speed sensors. Oh, I wish I had a suspension potentiometer so I could actually see how my bike was reacting to all of those inputs. And then you start adding that. So I think the best approach is build something that answers your question. At some point, I had an issue with engine braking, trying to understand how the rear was stepping out. And so I built just a tab for that to try to answer how my engine braking was set up. So yeah, try to start with a question, try to answer your question with your data, and then that's probably what's going to drive you to add more sensors.
Yeah, I think that's smart. Most people probably sort of go into it relatively blindly without a specific question in mind. But when you take that approach that you've just mentioned, it is going to drive all of the decision making there to try and get to the answer to that question. All right, Chloé, we'll move on here, and I'm really interested to get a bit of a sense of what your experience has been like being a female in a very male dominated industry. So, talk to us about that. Has there been any sort of disadvantages that you've come across based on that?
It's kind of a tricky question. I don't think it's ever been a problem until I became more of a professional. So until I graduated from school. One very funny anecdote: when I started in the paddocks, working as a data engineer, I was working for somebody that was pretty unknown and just working for a privateer. And towards the end of the season, these people were trying to make their deals for the next season, starting to have this conversation. And I was just always tagging along. And I realized that everybody around me was very open about having this very technical conversation next to me because they didn't know who I was. And they thought I didn't understand. It was probably, maybe I was just a random girlfriend. These don't really happen that much anymore. I think people are a little bit more guarded. So you have a little bit of that bias, like, oh, who's that? It's somebody who probably doesn't know. So I think in the OEM world, as a professional engineer, it's not so much of a problem, but you also have HR policies and you also have trainings against unconscious biases and everything. So people are very sensitive to having a good culture within. So sometimes you just have to be more assertive. I think the imposter syndrome is a little bit stronger in women. So, we have to learn to be a little bit more assertive. But I think it's something that we can control.
I think that imposter syndrome probably is more prevalent than maybe you think, and I don't know if that's purely just on the female side of things. So yeah,
Okay.
maybe that goes a little deeper than you probably think.
Yeah.
I'm guessing as well with your professional career in the OE world. I mean, you're a very educated person. You've got degrees, and you either have those or you don't. So if you've got them, it says to the employer, you know these topics inside and out, and really at that point, male, female, it shouldn't matter. So
Right.
I'm hoping that's the case, but
Right.
of course, maybe not always.
Right. In the paddocks, it's a little bit different because you have people that are coming, you can be a data engineer or data technician coming from a mechanical background where, you just have years of experience and you just gradually learn to use data acquisition system. I'm still pretty green. I've been in the paddocks it's going to be my 4th year. I just recently landed a deal with a premier team working for a 600 class. So I'll be managing 2 to 3 bikes and working with Mechatronic ECU. So I've grown pretty fast, and I think I just attribute that to. I think I'm glad that I have the degrees that I have. Let's put it that way. I've been able to say, and I've had to say a couple times, hey, this is literally my job. This is what I do for a living. So, that's happened a couple times. I think it's getting a lot better because now I'm known in the paddocks and people know what I'm able to do or know me. Actually, some people know me through Harley Davidson, through press events that we've had, through the racing teams. So what I do outside of racing is known, and there's credibility attached to that.
Yeah, absolutely, no doubt. Is there any advice you could give to potentially any of our female listeners, if we have any, to someone maybe looking to break into the industry? Yeah, any advice you could give in terms of how to approach that? I mean, get some degrees, maybe.
Yeah. So first of all, you have the female listeners. I know that for a fact. I mean, I'm one of them. Just go for what you want. If your reason for not going into engineering school is, oh, this is not for me, this is not for female, you're wrong. It's actually a really inclusive environment, especially when you're in school. And we're trying to cater more and more to outreach within companies. So the advantage, I would say, of being a female in the industry is you're more visible. And because you're more visible and you're a little bit more of a unicorn, you make those contacts with other female a lot more easily. So you actually are developing a network, I would say, a lot faster than men could be because you're so visible and because you're part of the minority. So to me, that's the advantage in the corporate environment. So school is not a problem. I had a really good time in school, and I think all of my female counterparts did too. And then when you start working, I think it's more of a benefit, for your career network than it is detriment.
Yeah. Okay. No, that makes sense. All right, Chloe, we'll move on and wrap this thing up. I've really appreciated your time here, and we want to respect that. And we will end with the same three questions we ask all of our guests. And the first of those is, what's next in the future for you?
I think I'm going to stay in this position that I'm in for quite a while. I'm just going to try to grow internally, grow in the paddocks. We've been talking about the fact that internal combustion engines could disappear at some point, and it's a probability. Harley Davidson is investing in EVs. So as much as I love combustion, I think I want to start focusing on control strategies. If you have an electric vehicle, it doesn't really matter. You're still going to have a torque delivery. You're still going to have power to manage. So getting into understanding understanding how ECUs actually work, all the control strategies behind that's really something that I'm trying to educate myself on. And if other advice, if you are an engineer and you're trying to study something, control strategies is a really cool way to make it into automotive. And yeah, I mean, really trying to get better at what I'm doing, get better in the paddock, get better at my job. It's a pretty unique and pretty cool situation to be in, to have my side gig, my hobby, and my job to all be about motorcycles.
Yeah, you've really built the perfect lifestyle for someone who's interested in motorsport and motorcycles. So all power to you. I mean, I think I've said this before in a number of our podcasts, but I mean, if you can do something for your job that you're passionate about, it's sort of, the old story, you'll never work a day in your life. And I do think that there's definitely some truth to that. Right, our next question, and we've already touched on the sort of the female element, but just in a more general sense, given your trajectory with your career and what you've achieved to date, is there any advice you'd give to maybe a younger version of yourself, one of our listeners, to help fast track that progress?
Yeah, tinker with things. I wish that when I had my first motorcycles at 8 years old, I had taken it apart. That would have been a really cool, first, a really good bonding experience with my parents and with my dad or my grandpa. And I would have probably gotten into engine so much faster because I would have tried to understand, everything that's behind it. But at the time, I don't know. I didn't really have any drive to do that. Maybe because I don't know. It was like farm stuff and mechanical stuff for farm stuff. And at the time, I was not interested in it, which is really interesting that I came back full circle. So motorcycles to me are really really cool because you have half of the tires numbers that you have on a car. You have half the brake system, so it's a lot cheaper to get into. A motorcycle has a very visible engine, so taking the engine apart doesn't require to have a hoist or anything, especially if you have a small motorcycle. So it's an engine and a motorcycle are very, very good teaching tools for anything mechanical. And it's small enough and accessible enough and cheap enough that you can do it on your own. So yeah, I would say just get whatever you're interested into and start taking it apart.
Yeah, I think that's really solid advice. I mean, looking back on sort of how my career progressed, I started out racing karts when I was about 12 or so, and I think I built my first kart engine at the age of 13 with a lot of help from my dad. And I mean, I didn't think too much of it at the time, but it was sort of starting to form those sort of concepts of all of the components inside the engine mechanically, how they interact and how they work together, which obviously looking at what I do now has really helped me out. So, I mean, yeah, if you've got the opportunity, absolutely, it's a powerful learning tool, and often, as you say, can be reasonably cost effective as well. Last question for today: if people want to follow you, find out more about what you're doing, how are they best to do so?
All right, so I do a lot of things through Instagram. I have my personal Instagram, which is engineerdissima, which comes from being an engineered and the most, which is the suffix issima. So this is more my personal page. It's very motorcycle centric because everything in my life is motorcycle centric, but it's more about my journey, where I am at the time, which racetrack I'm working on or working at, and then I have my more little business page, which is Unicorn Engineering, where I actually post my race build and the progress of it. Little things, little tips related to Aimsports, related to data acquisition systems, or little tips and tricks about the motorcycle that I'm building. So I'm building a Yamaha R6 race bike, and instrumenting it with all of the sensors that I can put my hand on. So yeah, if you're looking for learning what a motorcycle engineer does, then head to my personal page. If you're learning about engineering tips and tricks about motorcycle data acquisition or race race motorcycle build, then head to my professional page.
All right, perfect. We'll put a link to both of those accounts in the show notes as well, make it super easy for people to find you. But for now, we'll finish up. Really appreciate your time today, Chloé. It's been a really interesting and fairly wide-ranging discussion, so thanks for coming on board, and we wish you all the best for the future.
Thank you very much, and nice to meet you too.
If you enjoyed this episode of Tuned In with Chloé, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. Also, this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Luca from Australia, who has said, "It's a pleasure to listen to these and geek out on the in-depth level of detail. Great work, everyone." Well, thanks for your kind words there, Luca. And if you get in touch with the team with your t-shirt size and shipping details, we'll fire a fresh tee straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.